So we drop the irrelevant columns from the data frame like the ID, and we can also, I think, we can also drop the average glucose level from X set. We can do that later. And here we are just removing the ID variable, and we are imputing BMI by the mean of the rest of the in BMI of the individuals. And then we extract the response variable from the clean data, and then the X variable, the X data frame consisting all other variables excluding the average glucose level and average glucose level 2 and the stroke variable. So then we can convert the variables to the dummies. So X encoded PD get dummies, then X drop first means we are uh, just ignoring the first category and making dummies for the other categories. So you can see, for example, for male, for gender, we had male, female, and others. So we get two dummies for male and others, keeping females as the base category. And similarly, we can see dummies for other qualitative variables. So just run the X data set. So this is just used to see X as a list to see how many dummies we have created. You can see, for example, for smoking, we have 3 dummies. For urban, we have urban and rural status, we have only 1 dummy. So you can, this will be automatically done by the PD get dummies option command. And then we can add a constant column for including the intercept in the X set, and that is SM add constant and X encoded. So it will automatically encode the in the X encoded data frame. It will create a column of constants consisting only once. And then we can convert that again all the variables to float using, and this is X with constant data frame as type float. So it will convert all the variables to the numeric. It is not working. I think we have missed some package. We can import this SM statistical models. So we need to import states models. You can just write it as extension, or you can just write as SM. So let's try whether it will. It's, I think, working. So now you can, we should be able to run this. It's still not coming. I think at constant. There should be this library, I think. Let me check for this library. At constant, let me check. So we can just import statsmodel.api as SM, and maybe we can import with this, and let's check. Yes, it's now working. So we have just added a constant and converted it to the numeric. And then we have already run this here. Sorry. So you could just add this. I think we have already done this. And then we also used state model dot formula as SMF, and that is used for running the linear regression model. So gamma regression model. So we are just running a gamma model with sm.glm, and then dependent variable and the data frame consisting the a set of predictors, and family is sm.families.gamma, and then family links log means we are using log link function, and gamma results gamma model fit, and then we will get the summary of the result. So here you can see the summary of the result. The constant is 4.20 and age has 0.0039. So this basically tells the uh, 1 unit change in X will cause a percentage change in Y. So we need to just uh, exponentiate this value. That will basically the ratio of the log, and we are just taking logarithm after exponentiation. um, Taking exponentiation on both sides, we get the uh, ratio of the two means. So the mean change is basically we are just the mean change uh, in Y with 1 unit change in X. Uh, so we need to convert it into percentage, and then when we get in percentage, we need to see whether it's increasing or decreasing. If, for example, if these values are in negative, it means it is below 100. So we need to check how much the mean ratio has the ratio of the mean has decreased from 100%, and if it's greater than 1 or greater than 100, then we will interpret it as increase in the value with increase in the value of X, increase in the dependent variable, the ratio of the dependent variable with increase in X. So we will discuss this in detail. For that, we need to import numpy as np. We have also the standard error and the z value and the p value and the 95% confidence intervals. So you can convert this into exponentiated coefficients, and we can also represent the confidence interval into exponentiation. So how we can do this, we will discuss. Here, examine the summary results. We have already printed, and then you can just print summary regression models like this. And then you can identify significant variables with p-value less than 0.05. I will just check this. We can do this on a separate code cell. So this is basically the values with significant results, significant p-values. So we have significant p-values for constant, age, hypertension, and all these variables. And then we just interpret the coefficients with which is for log link with its exponentiated coefficient is the ratio of expected mean for a 1 unit change in the predictor. So For variables with p-value insignificant, where p-values are significant, if variable is equal to constant, continue, just skip, we will skip the constant, we don't need to do that. And coefficients in the set uh, gamma results parameters and the VAR. So we will get the coefficients, and then we will get the percentage change, that is exponentiated coefficient minus 1 and multiply by 100, and we will get the variable name and coefficient and p-value. If coefficient is greater than 0, it means positive. For a one, in this way we will just uh, interpret as for a 1 unit increase in X, the expected mean glucose level, the expected mean value of Y is estimated to increase by approximately this percent, for example, 5%. So we'll just run this result. Else we will, in case of negative, we will just interpret as the 1 unit increase in X, the expected mean is estimated to decrease by this. So it's 0.039 coefficient. So p-value is 0.0000, and when we exponentiated this, we get this value 0.40. This is exponentiated and subtracted from 1, so it is 0.40. It means 0.4% increase. Zero point 0.4, not 40%. 0.4 increase with 1 unit increase in age. For example, with a 1 year age, the average glucose level will be increased with 0.4%, which is a very slight increase, although it's coming statistically significant. Maybe it's due to small sample size. And in similar way, keeping all other variables as constant. So this would be in the interpretation of the beta corresponding to the age. So age is a quantitative variable, so we just say with 1 unit in 1 unit increase in age, means 1 year in change in age, it will increase, that expected mean will be increased by 0.4%. And then for example, for hypertension status, the mean is 13%, the mean change is 13%. So it is again, I think the positive, you can see for a 1 unit increase in hypertension, the expected mean glucose level is estimated to increase by approximately 13.69%. So this is exponentiated value of this. This is positive. It means it's causing increase. So what is the hypertension? Hypertension is a dummy variable with 1. With hypertension, 0 means no hypertension. So people with hypertension has an approximately 13.69% higher average glucose level than those who has no hypertension. So this is the interpretation for a categorical variable. Similarly, we can for here you are comparing, we can say that the average glucose level, this is also positive, so the average glucose level is 3.85% higher in male as compared to female, as female is the reference category. So we just compare with the reference category and keeping all other variables as constant. So this is the interpretation of the coefficients in a gamma regression. Thank you.